SpaceX just exposed a landing plan that could save astronauts stranded on the moon. 35 meters, that's how far the crew must descend on Starship's elevator. NASA's own report is blunt. If that elevator fails, there is no backup, no other way down. Now, one new idea could cut that fall to just 5 meters. Could this single change decide the fate of the next moon landing? Stay with me. Let's start with the number that should worry you. 35 meters. That's roughly the height of a 12-story building. Now picture an astronaut, wrapped in a pressurized suit that weighs more than they do, standing at the top of that building on the moon, with one job left to do: get down safely. For years, SpaceX's answer was simple: an elevator. A platform that lowers astronauts along the outside of Starship, all the way from the crew cabin near the top, down to the gray dust below. On paper, it sounds elegant. In practice, it's one of the most dangerous unsolved problems in the entire Artemis program. NASA doesn't bury this concern in technical footnotes. It's spelled out directly in an Office of Inspector General report, and the wording is unusually blunt for a government document. The report states that if the elevator fails, there is currently no other method for the crew to enter the vehicle from the surface. No other way. Not a slower way. Not a backup procedure. None. Think about what that actually means in practice. If a cable jams, if a motor stalls, if lunar dust works its way into a mechanical joint at exactly the wrong moment, 2 astronauts could be standing on the moon, fully suited, fully trained, with their spacecraft sitting right in front of them, and absolutely no way to climb back inside. That single sentence in NASA's report is the reason this entire story exists. So the real question becomes, how does an agency that put a man on the moon over 50 years ago end up facing a risk this basic all over again? Why this is happening now? The answer has nothing to do with carelessness. It has everything to do with ambition outrunning convenience. Look at the numbers side by side. The Apollo lunar module stood about 7 meters tall. Astronauts stepped down a short ladder, dropped the final stretch in low gravity, and that was the entire exit procedure. Blue Origin's upcoming Blue Moon Mark II, the crewed lander competing for future Artemis missions, comes in around 16 meters, tall but still within reach of a conventional ladder system. Starship HLS breaks that pattern completely. It isn't a purpose-built lander shrunk down for efficiency. It's a modified upper stage of the most powerful launch system ever constructed, repurposed to touch down on another world. That heritage gives it enormous cargo capacity and enormous livable volume once it's on the surface. But it also means the crew cabin sits more than twice as high as Blue Moon, and 5 times higher than the vehicle that carried Neil Armstrong. Here's the trade-off in its simplest form. A bigger vehicle means more capability, more cargo, more room to work once it lands. But it also means a longer, riskier descent to actually get the crew out. Every advantage Starship gains from its size becomes a liability the instant astronauts need to leave it. And height isn't the only complication. The moon adds variables that no elevator test on Earth can fully replicate. Lunar gravity is about 1/6 of Earth's, which changes how every motion behaves, including subtle swings or vibrations in a suspended platform. A shift in crew weight, a few degrees of uneven ground beneath the landing legs, even fine lunar regolith working its way into a mechanical track. All of it introduces unpredictability that engineers can model but never fully guarantee. Because of this, NASA has set a hard requirement. The system must tolerate at least one full failure without producing a catastrophic outcome. That's not a guideline. That's the line SpaceX has to cross before any human climbs aboard this vehicle. So now the pressure is real, and it's about to get heavier. What's actually at stake? This isn't just a footnote affecting 2 astronauts on a single mission. It's a pressure point sitting underneath the entire Artemis program. If the elevator risk isn't resolved with total confidence, it doesn't just delay one landing date. It threatens the credibility of the human landing system program as a whole, the very centerpiece of America's plan to return to the moon for the first time since 1972. Every slip here ripples outward, touching the Artemis 3 timeline, touching how international partners judge the seriousness of the program, and touching how the rest of the world reads America's commitment to staying ahead in space. and someone else is watching closely. China has been steadily building its own crewed lunar program with its own target dates for landing near the South Pole. In a race like this, a technical setback isn't just an engineering footnote. It's a strategic opening for a competitor. So SpaceX is left holding a genuinely difficult question. How do you keep every benefit that comes from building an enormous high-capacity lander while removing the single biggest safety flaw that comes from making it enormous in the first place? Most engineering teams facing this question would reach for the obvious fix. Add more backup motors, more redundant cables, more fail-safes stacked on top of fail-safes. Layer after layer of protection bolted onto the same flawed system. SpaceX appears to be doing something different. And this is where the story stops being a list of problems and starts being a story about a solution almost nobody outside the engineering community is talking about yet. The unexpected fix. The concept is called sideways landing, and the logic behind it is almost deceptively simple. Don't build a better elevator. Eliminate the need for one entirely. Here's how it would work. Starship would descend vertically for most of its approach, exactly the way every Falcon and Starship landing has worked so far. But just before touchdown, instead of settling straight down onto extended legs, the vehicle would begin rotating, tipping itself from a standing position into a horizontal one. Gimbaled main engines, combined with additional thrusters positioned along the midsection, would control that fall, guiding the spacecraft from vertical to flat in a single controlled motion. A skyscraper that, instead of remaining upright after landing, gently lowers itself onto its side. That's effectively the outcome this maneuver produces. And the payoff is enormous. Once Starship is lying horizontally, the crew hatch sits only about 4 to 5 meters above the surface, not 35 meters. 5. That's roughly the height of a single garage door. Suddenly, instead of a fragile motorized elevator carrying the full weight of crew safety, astronauts could exit using something far closer to a simple ladder or a short ramp, similar in spirit to systems already proven on past lunar missions. Does that sound familiar? It should. NASA briefly studied something close to this years ago, under a concept sometimes referred to as Moonbase Alpha, where a horizontal Starship wasn't just a lander, it was treated as an instant habitat the moment it touched down. That old idea is resurfacing now, but this time it's being evaluated specifically as a direct fix for one of NASA's most serious documented safety risks. This is where most coverage of this story stops. A clever idea, a shorter drop, problem solved. But that's not the full picture. And the part that gets left out is exactly the part that matters most. The catch. Nobody saw coming. Here's the twist. Sideways landing doesn't remove risk. It relocates it. Start with timing. The thrusters guiding that rotation from vertical to horizontal have to fire with extreme precision. Too early, and the vehicle could slam into the surface before the rotation finishes. Too late, and the main engines, still firing to slow the descent, could end up working against the very maneuver they're supposed to support. There is a narrow window where this has to happen correctly, and lunar landings don't offer a second attempt. Then there's structural stress, a problem that's easy to underestimate. When Starship is standing upright, its weight pushes straight down through landing legs designed for exactly that load. Lay the same vehicle on its side, and that weight spreads across a much larger surface area, an area that wasn't built to bear weight that way. On uneven lunar terrain, where the ground itself isn't flat or predictable, that load becomes uneven too. Pressure builds unevenly across the hull, raising the risk of structural deformation in a vehicle that was engineered from the very beginning to operate vertically. And that vertical assumption runs deeper than the outer shell. Every internal system inside Starship, fuel lines, cargo racks, life support routing, was designed around the idea that the vehicle would always be standing up. Tip that structure 90 degrees, and suddenly fuel might not flow where it's supposed to. Equipment bolted in place for a vertical orientation could shift unexpectedly. None of this is fatal on its own. But it means sideways landing isn't a simple fix bolted onto the existing design. It's closer to a second engineering problem, layered on top of the first one. So here's the real question worth sitting with. Is trading a known risk? an elevator that could fail for a new and less tested risk? A horizontal landing that introduces fresh engineering unknowns actually progress, or is it just moving the danger somewhere harder to see? Why this might actually be a good sign. Here's where this story takes a turn. Most coverage misses entirely, and where there's a real case for optimism, not despair. In aerospace engineering, there's a principle worth understanding before judging this debate. A single point of failure, one part that can take down an entire mission if it breaks, is treated as the worst possible design flaw in any human-rated system. The elevator, as it currently exists, is exactly that. One mechanism, one failure mode, one catastrophic outcome if it goes wrong. What SpaceX is doing by even considering sideways landing isn't avoidance. It's the opposite. It's an organization willing to question its own core architecture, rather than patch around a flaw with extra backup motors and call it solved. That's a meaningfully different posture than simply adding redundancy and hoping for the best. And there's precedent for this kind of mid-program pivot working out. Early Falcon 9 booster landings failed repeatedly before SpaceX figured out the right combination of grid fins, throttle control, and landing leg geometry. Each failure fed directly into the next design. The willingness to rebuild rather than patch is part of why SpaceX now lands boosters routinely, something that seemed nearly impossible a decade ago. That doesn't guarantee sideways landing succeeds. It might not. NASA's current published architecture still shows Starship HLS using landing legs and a vertical configuration, which tells us this remains an open question, not a finalized decision. But it does mean the elevator risk is being treated with the seriousness NASA's own report demanded, not quietly minimized to keep a launch schedule on track. The bigger picture, nobody connects. Here's the part of this story that almost never gets mentioned, and it changes how the entire elevator debate should be read. This isn't just about getting two astronauts safely down to the surface for a short visit. NASA's ambitions for the lunar South Pole have grown dramatically beyond a single landing. Recent statements from the agency describe a future base, spanning hundreds of square miles, with habitats positioned on elevated terrain for sunlight, power systems set a kilometer or more away for radiation safety, and a layout that increasingly resembles early urban planning rather than a temporary outpost. Now connect that back to the elevator problem. A crew exit system isn't just a one-time safety feature for a single mission. If NASA is serious about a permanent, expanding lunar presence, astronauts will be entering and exiting these vehicles repeatedly, year after year, mission after mission. A fragile, single point of failure elevator doesn't just risk one crew. It becomes a recurring liability built into the foundation of an entire settlement. Seen this way, the sideways landing debate isn't a narrow engineering footnote. It's a preview of the standard SpaceX will need for every Starship that touches down at a future lunar base for years to come. Get this wrong now, on the very first crewed landing, and the consequences compound across every mission that follows. That's the part the surface-level version of this story leaves out. And it's exactly why this decision deserves far more attention than a single paragraph buried inside a government oversight report. NASA's own roadmap gives a rough sense of timing pressure. Artemis 3 is currently targeted for around mid-2027, with critical docking demonstrations between Orion and the chosen lunar lander required before that mission can move forward. That doesn't leave SpaceX an unlimited runway to finalize this decision. Two paths sit on the table right now. Keep refining the current elevator with deeper redundancy, more backup motors, more fail-safe layers, accepting a known risk that's at least well understood. Or commit to sideways landing, accepting a newer set of structural and timing challenges in exchange for cutting the fall from 35 meters down to 5. Neither option is free of risk. That's the part worth remembering before drawing any conclusion here. This isn't a story about a problem being solved. It's a story about an agency and a company weighing two different kinds of danger, in public, with the stakes as high as they've ever been for an American return to the moon. The part most people never ask. There's one more angle worth sitting with before moving on, because it explains why this debate is happening so publicly in the first place. NASA didn't have to put this risk in writing. Government oversight reports can be vague when they need to be, full of careful language designed to avoid alarming anyone. Instead, the Inspector General's report names the elevator directly as a top program risk, on the record, for anyone willing to read it. That's not standard caution. That's a signal that someone inside the program believed this issue was serious enough to demand public accountability, not just an internal memo buried in a filing cabinet. Compare that to how spaceflight risk used to be handled. Decades ago, problems like this often stayed inside closed engineering reviews until something went wrong publicly. The fact that this conversation is happening out in the open, years before a single astronaut steps near the vehicle, says something about how differently this program is being run. Whether that openness was NASA's choice, SpaceX's choice, or simply unavoidable given how much public attention Starship draws, the result is the same. A flaw that might once have stayed hidden until launch day is instead being argued over, tested, and redesigned years in advance. That's worth remembering the next time a headline makes this sound like a crisis. A flaw being discussed loudly, in public, with NASA demanding fixes before crew ever boards the vehicle, isn't a sign of a broken program. In aerospace, it's often the clearest sign of a program still working exactly the way it's supposed to. That is the real engineering question, not yet answered. Thank you for analyzing it with us. Like, share, comment, and subscribe to the Space Brief. One more click, the end screen is right there.